great. Thanks very much. The magnetotelluric program of EarthScope is quite similar in concept to the seismic part of USArray. We have three elements to it. There's a magnetotelluric transportable array, a magnetotelluric backbone, which is similar in concept to the reference network, and a magnetotelluric flex array. So the configuration we use for the transportable array and the backbone array is by deploying a series of long period or low frequency sampling magnetotelluric instruments. These are providing information about the electrical resistivity structure starting at mid-crust depths. And for the transportable array with the frequency band we use, we see into the upper mantle. In general, for people who are relatively new to MT, we're measuring the orthogonal horizontal components of the electric field using a cross-dipole receiver system about 100 meters on a side heading oriented north-south and east-west, and also three-axis magnetic field sensors measuring the horizontal and vertical components of the magnetic field. For the TA, it's a very light installation, generally takes a field crew of a couple people, and we are done with a site completely in anywhere from 5 days to 30 days, and then we move on to the next site. For the backbone, these installations using equivalent instrumentation but configured differently, buried underground for thermal stability, generally using longer dipole receivers with telemetry, unlike our transportable array, which doesn't telemeter. I have been operating since 2008 or before, depending on the station. These are configured to get us deeper penetration into the upper mantle because we get even longer period data from these. And there's an equivalence between frequency and depth. The low frequencies penetrate deeper into the Earth than the high frequencies. Finally, the flex array configuration, we're generally flexible in the sense that we use two different styles of instrumentation. On the left, we're seeing identical instrumentation to the MT transportable array, so it's a long period instrumentation. So again, intrinsically with the kind of systems we use, we're able to see mid-crustal to upper mantle depths with this kind of configuration. On the right, we also have a new class of instrumentation that's wideband or ultra-wideband. In fact, in one configuration, we can sample at speeds as high as megahertz, and that gets us near surface. So we can actually configure flex array experiments to do anything from near surface geophysics down into the upper mantle. And this is just illustrating some of the recent work we've been doing with this style of instrumentation in the winter at Newberry Volcano in Oregon, which is an enhanced geothermal systems project. That's not an NSF. These two are not NSF-funded projects. They're DOE. And then the upper right, this is me in the desert in Saudi Arabia in October looking for groundwater, again, in a flex array style. That's kind of illustrative of how quickly you can operate. The average station occupation time was 2.5 hours. And that got us information in the top 7 or 8 kilometers below the surface. Okay, so those are the three components. Again, for people who are unfamiliar with MT, let's just talk about MT as the other 5 seismic channels, because although the physics is rather different, we're not doing a wave equation, a seismic wave equation. This is more of a diffusive phenomenon. The goal is equivalent. We're imaging the crust and the mantle. So we start with the top panel is the north-south electric field, then the east-west electric field, and then down the rows, north-south, east-west, and vertical magnetic fields. Looking at the workflow on the right, we start with the MT time series, going through various forms of signal processing. We end up with a dead screen. There we go, for whatever reason. We end up with a series of transfer functions relating the electric and magnetic fields and the various components of the magnetic fields to each other that we call the impedance tensor and the tippers. The impedance tensor is a 2x2 complex valued frequency-dependent function, and that and these magnetic field transfer functions, a form of which are called tippers, are used in the inversions to give us either 2D or 3D models. And our normal mode for transportable array work is 3D. So in an isolated world, you then take it from the models, which are, say, 3D models of electrical resistivity structure in the mid-crust through upper mantle or below, and there's an interpretation phase. Now, of course, in seismic, there's an equivalent process, and you end up with the inversion phase, or other geophysical data sets and geological data sets, for that matter, where you have models. This is basically to illustrate that increasingly, and this is now standard practice in the exploration and reservoir monitoring industries, these are coupled processes. You don't do MT in isolation. You don't do seismic so much in isolation. You, in fact, have a feedback between the two, and you end up getting, to illustrate, a much stronger set of constraints. For instance, if we look at MT, our fundamental physical property is the electrical resistivity. So we're getting nice 3D models of that. What does that mean in terms of the properties that we're really interested in? Well, resistivity, of course, is a bulk property of the rocks. It's also dependent on temperature and composition, but really it's supremely sensitive to the presence of interconnected fluids and melts, the presence of, say, hydrogen, volatiles, depending on where you are in the tectonic framework. It can be quite sensitive to the presence of carbon films and sulfides that may speak to the accretionary and deformational history of the lithosphere. So it's complicated. You can't uniquely say what's what just from this one parameter. You start adding, this is a badly mangled one, but anyway, you start adding seismic to the mix, and then you begin to get more structural controls, more physical and state controls on the system, and that refines both sets of interpretations. Boy, this has become horrible, but you get the idea. We then start adding gravity, and we do this a lot in geothermal because you can begin to get independent of seismic estimates on density, which helps constrain the seismic. It feeds back into the MT. The uncertainty starts collapsing into a smaller region in terms of the physical properties you're really interested in teasing out. If you can add additional elements in a dynamic system, such as ground deformation on the tectonic scale, GPS, but also on the finer scale, we use both satellite-based INSAR and also ground-based true aperture interferometric radars. We can look at dynamic ground elevation. We do this a lot in geothermal stimulations, and we believe we'll be able to apply this to fracking problems. So it's just to illustrate, by putting all these methods together, you get a great complementarity and much tighter interpretation on what you're really interested in. And let's not forget petrology and geochemistry and fluid chemistry and complementary geophysics. So that's the direction we're going into. Okay, let's talk specifics now. Where are we in the global scheme of things? For the transportable array from 2006 to 2012, we had completed 463 MT transportable array stations in the continental US. Our colleagues in Canada, led by Martin Unsworth, had also completed 95 Canadian stations on a complementary grid in Alberta, and these also exist in the IRIS DMC as part of the EarthScope, general EarthScope data set. You'll notice these green dots, those are the MT stations that are already in the DMC from the transportable and backbone arrays. Where we are now is in the midcontinent, and you'll notice some faint white dots south of the green dots, the array we had completed by 2012, sweeping to the south and then east into and north into Michigan. That's where we're operating right now. So we have field crews in the field. We're targeting 100 station completions for this year. Backbone's been operating since 2008 or before. We're in the middle of planning to move into a different operating mode for our backbone that we're calling the adaptive backbone starting next year, where we'll take our existing stations, which we think have extracted all the information we hope to get out of them, and to move them to other locations in a different operating mode. The flex array, there are currently 3 MT flex array experiments underway, and I'll talk about them in more detail. But one of them, MOCA, you'll notice in the top left here off the Cascadia margin, there are white circles extending offshore and also onshore. There are 75 of these on land and 60 offshore. That's the MOCA experiment. Immediately to the northeast of those is a tighter cluster of white circles adjoining that array. That's a project called IMUSH, and there are 150 wideband stations, flex array stations. And then in the Rio Grande area, there are 132 long period stations for another experiment. I'll talk about those in more detail later. This has become totally useless on this computer. That's really depressing. Oh well. So, well, I'll wing it. So all my bars are gone. Where we are, you'll notice these vertical white numbers. They should be bars. They're telling us the total number of stations we project to have completed over time. And you'll notice that by the end of 2012, we will have completed 493 magnetotelluric transportable array stations. That blue line with the reddish numbers represents the percentage of the continental U.S. we will have completed at that point. So by the end of this, the end of last year, we would have completed 29% of the continental U.S. with the transportable array. The end of this year, it'll be 35% if we're on track. And going through what we are projecting under the assumption that the next 5-year EarthScope O&M period continues as planned, we will have completed 57% of the continental U.S. By the end of 2018 if we maintain the 70-kilometer spacing array. Last year we had, unfortunately this is obscured, we hit our peak of completing 115 new station installations plus 4 station reoccupations. So that's kind of our current capacity during a normal field season. Okay, let's look at some issues related to the TA and the backbone. This is sort of a trip down memory lane because this was presented 2 years ago at the last EarthScope National Meeting as a keynote by Anna Kelbert. And this is the results along Yellowstone Snake River Plain. So just reminding people of this, in the top left, we're looking at a map view of the electrical resistivity. Red is extremely conductive. Blue is extremely resistive. This is mid-crust at 22 to 26 kilometers. If we look to the top right, it's a deeper section at 50 to 58 kilometers. And you can just about see the boxes here. This is Wyoming, the corner of Wyoming where the Yellowstone is. And then we can track it down from there along the Snake River Plain. Or if you prefer in cross-section, it's a little easier to see. Why? So we're on a section going from the northeast to the southwest through the Yellowstone caldera. So on the bottom left, Y, that little Y represents the Yellowstone. And then X happens to be a crossing point, which I can't even see from here, but it's somewhere over there where we have a couple of profiles cross. Let's just look at the left-hand side. You'll notice this striking electrical conductor to the west of Yellowstone, steepening to the west and eventually reaching moho and sub-moho depths in the upper mantle as you bob along the Snake River Plain. So that's a striking feature. Directly beneath Yellowstone, it's absent. So a couple of important points for the magnetotelluric transportable array configuration. We are blind to structure in the upper 10 or 12 kilometers because of the frequencies we're using. So until we can get back into Yellowstone and have a much denser array configured with wideband instruments, we're not going to have any information about that upper crustal section. But once we hit the mid-crust, we know there's no high conductor directly beneath the caldera, which is quite an interesting observation. When you look at some of the seismic results, you might have expected to see that. And the interpretation is there is an absence of significant amounts of interconnected melt. If there was a lot of interconnected melt, it would tend to be conductive. However, we're seeing the kind of evidence of that further along the Snake River Plain, where you can see the high conductive area, which could be associated with hydrothermal fluids and a degree of melting. So let me just remind people of that. Now let's look at some of the more recent results. This is now in the northwest quadrant of the U.S., so going all the way from the Pacific coast on the U.S.-Canada border to the edge of the, just into the Great Plains in Montana, and Wyoming, and then extending down to just north of Sacramento, California on the bottom left, and east into past the northern part of the Great Basin, et cetera. And you're looking at different crustal depths, starting at 11 to 14 kilometers, so kind of this mid-crust, then down to 31 to 37 as we go right, 94 to 110, so we're now well into the upper mantle, and down to as great as 236 kilometers on the bottom right. Again, red is extremely conductive and blue is resistive. And let me just quickly highlight some features. You'll notice there's this streaky appearance, and the scale length of the spacing between these streaks is quite similar to the station spacing. We have a 70-kilometer grid. Now, these elongate zones are more or less aligned with the seismic fast axis, so that's notable. At this scale, we would be unable to distinguish between true anisotropy in electrical conduction or fine striated structure in electrical conduction. So this is just a limitation of our station spacing. But this is consistent, whether it is anisotropy or striations, it's consistent with alignment of null flows that we believe could be induced by slab rollback. So that's the first note. Next, you'll notice these highlighted, highly conductive regions, the high lava plains, the Snake River Plain, Northern Basin, and Range. And these conductive zones are attributed to underplating by hybridized magmas and any saline fluids that would be exsolved. If we look further to the east, we have the cratonic areas, the Medicine Hat Block on the top, and the Wyoming Craton. They're thick and they're electrically resistive. And bridging between the two is the Great Falls Tectonic Zone, which is interpreted as a suture and one that's rich in conductive metasediments. If we look toward the west, where we have relict oceanic lithosphere, there are these electrically resistive blocks. If you look, it's very difficult for me to see here, but we're sort of in this region here, going just south of Rangalia and transitioning into northern and southern Silesia. We see these electrically resistive zones in Silesia terrain, and also beneath the Coast Range, and also in the Columbia River plateau. And again, this is quite consistent with what we understand about the accretionary history of these semi-rigid crustal blocks. If we go further east and deeper, there's this really interesting deep vertical resistive feature. You see the SC with the fine dashed white line around that, and that happens to be coincident with this now well-known seismically fast slab curtain beneath Idaho. So it certainly is coincident with Schmatt and Humphrey's interpretations of stranded Farallon lithosphere. So we're seeing that in the electrical models as well. Okay, moving on. If we do a cross-section, one of many possible cross-sections, this one is from 42.2 degrees north, starting at the Pacific and going into Cratonic North America. You'll notice there's this very fine, short, dashed black line, and that denotes the top of the subducting plate. There's a dashed white line that kind of goes along here, and that's an estimate of the continental moho based on Alan Levander's work with receiver functions. And then this is our interpretation of the electrical lithosphere-asthenosphere boundary. If you go to the back arc and immediately to the east, so we're in this region, and look at the resistivities, we find they're consistent with thermal lithosphere. That's 50 to 60 kilometers thick in the active tectonic part of North America. As we move east into the Cratonic North America, see it thickens a great deal, and we get depths of 200 to 250 kilometers under these more stable areas. Again, back into the west in the active tectonic region, the asthenospheric resistivities, when we get down to depths of 150 to 200 kilometers, are consistent with the resistivities known from lab work of dry olivine. As we get below that into this more conductive region, if we stick with an olivine mantle, we require a degree of hydration, about 350 parts per million. Moving to the stable area to the east, we get, in fact, very high conductivities beneath the craton. Now, there are a couple of interpretations. One is an even higher level of hydration beneath the craton, but there's a real advisory here. We're right at the edge of our data. We're at the edge of the model. We know that there's a highly conductive feature in the Great Plains of North American Central Plains anomaly. This is a huge feature. We're probably seeing some influence from not only that, but some edge effects and some resolution limits. So until we push the array further into that zone, we'll be a little bit conservative about the interpretation of the higher levels of hydration until we can confirm that. Okay, looking now at the same model, but in a more of a volume rendering, there are a few very interesting features to point out. You'll notice these arrows are pointing to these features BA 1, 2, and 3. These are conductive features. They're rather plume-like. They're connected to this deeper asthenospheric layer to the east, and the interpretation is this is consistent with subduction-driven upwelling of what are going to be hot, hydrated, and possibly melted or partially melted asthenospheric mantle. Let's just sort of take a tour through that and see if this works. Oh, miracles happen. Okay. So again, Wyoming Craton appearing, the Medicine Hat Block, cratonic areas, and we can see that they're separated from other resistive blocks by these suture and or shear zones that are Proterozoic, and they've got probably a great deal of, or a reasonable fraction anyway, of carbon films and possibly sulfides. And then when we get into the west, we can see, we're just about to lose it, this very resistive, about to be coming into view here, this very resistive block along the coast that maps into the downgoing slab, basically, the influence of the downgoing slab, which is resistive, and then below the Cascade Volcanic Arc and into the back arc, this upwelling conductor. Okay, what are we doing right now? So right now we're in the midcontinent. In the center, there's the familiar map by Marshak showing the major faults and the major structures in the midcontinent rift system in red. And so this has been the target of this array as the midcontinent rift system. You know, we've completed this coverage here, so we have the main lobe of the MCR, and by the end of this field season, we should be picking up the weak, you know, at least as far as the gravity signature, the weaker arm of the midcontinent rift system. I should mention, actually I'll go back to that very quickly. When we set out to do this, it wasn't clear how strong the MT signature might be of conductivity heterogeneities in the midcontinent. It was pretty much unknown territory. I can tell you with great confidence the degree of heterogeneity in the MT data here is at least as big as it is in tectonic North America. So it was far from a boring area. So we're getting some very nice data from there. Okay, now one of the nice things about having the transportable arrays, it allows us to put existing data sets into a bigger context. So McGarry et al. Have been revisiting some historical data, the canonical big MT experiment of the mid-1980s, which was MSLAB, which was a two-dimensional profile, included a two-dimensional profile offshore, onshore, entering the shoreline at Lincoln City, Oregon, and connecting into Mount Jefferson, and then augmented with some of the MTTA data. And this is now an interpretation, but on the top, I think this blows up here. Okay, so we have a seismic image on the top showing, you know, this if we look down at around 40 kilometers, we can see the continental moho in the east, and in the west, you can see the dipping low velocity layer as the you know, the slab starts to go through its conversion. You get eclogite, and one of course, the features of that is the dehydration and then the serpentinization above it in the wedge. Okay, so we see that process, or at least the seismic data are very consistent with that process. If we look to the bottom model, which is a 2D inverse model of the M-slab data now, we see, in fact, a very similar picture emerging, and I'll just point out this kind of conductive feature here, which the authors have interpreted to be, again, the signature of the fluids released from the downgoing slab. And you clearly want me to... Okay. This is just very, because I'm nearly done. Very quickly, we're seeing the three current transportable array studies and a completed one, which is the CAFE-MT line by McGarry et al. And again, the MT interpretation showing this upwelling conductor, which they have interpreted to be the signature of the dehydration and the serpentinization. And let me wrap up. So everyone go on break. Our current other projects are MOCA, which is an onshore-offshore MT experiment. These white circles in the reddish box, and that is currently underway in the field. And the idea here is to look at not only the segmentation of the Cascadia margin in Silesia and the transition to Rangalia in more detail, but to look at the fluid question in 3D. And then here, IMUSH, which is high-resolution MT and seismic active and passive experiment to look at the fine-scale structure of the magma beneath the southern Washington Cascades volcanic arc. So that's it's very busy right now. There's a lot going on in MT, and things are hopping. So we encourage people to consider how the MT data and the seismic data and all these other data sets can actually be synthesized into a coherent whole. So thank you.